So I'm Stefano Ermon. I'm an assistant professor in the computer science department. And today I'm going to talk about some of the research we've been doing in my group on combining the latest developments in computer vision and machine learning with high-resolution satellite images to track economic development and address sustainability challenges. So let me start with some motivation. Our society today is facing a number of very formidable challenges to sustainable development. There is close to 1 billion people around the world living in extreme poverty, hundreds of millions of people that don't have enough to eat every day. Climate change is threatening the survival of many societies around the planet. We're going to have to find new sources of clean and affordable energy, find ways to reduce inequalities between developed and developing countries, and so forth. Now here you can see the 17 Sustainable Development Goals that were identified by the United Nations as sort of being the key priorities that the international community should be focusing on in the next 15 years or so. Clearly, these are very, very important problems, but they're also really, really challenging. And one of the reasons is that it's easy to set a target, to set a goal, but what we really need is a way to measure progress toward these targets. And unfortunately, for a lot of these problems, we just don't have good enough data to figure out whether we're making progress, figure out whether policies are working or not, and generally inform research to try to understand how these very important problems work. So if we look at poverty, for example, which is the number one problem on this list, the way we typically collect data on poverty is through nationally representative surveys. These surveys are expensive, and as a result, they are done very, very infrequently. So here you can see a map of the African continent, and it's showing the availability of nationally representative surveys in the decade from 2000 to 2010. The color here corresponds to how many surveys were done in that country in that decade. You can see many of the countries are white or a very, very light color, meaning that that country didn't do any survey or very, very few surveys in that entire decade. So as you can expect, with this kind of data, it's very, very hard to, if we don't even know how many poor people there are there in the world, where they live, it's very, very hard to track progress, inform policy and research, and so forth. Now, on the positive side, these days we're getting access to very high-resolution satellite images from pretty much every corner of the world. And these images contain a lot of information about various kinds of socioeconomic indicators that we might want to track over space and time. I know you can see it there, maybe a busy shipping yard where you can almost, the resolution is good enough that you can almost count the containers, how many ships are there. You can see information about economic activities, about mines, agricultural fields. You can see information about infrastructure, houses, what kind of vehicles people have, what kind of roads people have. So clearly there is a lot of information contained in these images. Now these days it's not just images. These days you can even get access to high-resolution videos from space. This is something that is commercially available today. And obviously there's clearly a lot of useful information in here. The question is, how do we actually extract it? How do we actually make sense of this in a scalable way? And so as Bill and Steve mentioned, this is really an exciting time to start thinking about making sense of all these images in an automated way because of the progress that we've seen in the last few years in machine learning, computer vision, and deep learning. We've gotten pretty good at a number of visual and perceptual tasks like recognizing and classifying different kinds of images, tracking, localizing and tracking objects in images and videos, and generally try to understand the meaning of scenes and videos. So I think it's really, really an exciting time to think about what we can do if we combine this new data that is becoming available globally. It's getting increasingly better, increasingly more accurate, increasingly cheap. There are a number of private companies that are entering the market that are driving the costs down. So they're creating this very, very rich data. And we can combine it with these new capabilities that we have for making sense of this at scale. And so it's really an exciting time to think about combining these two ideas and see what we can do if we have a way to scalably understand and track what's going on at a global scale in a very, very fine-grained and inexpensive way. Now, the challenge, so ideally we would like to kind of combine these new inputs that we have access to, so high-resolution satellite images, combine them with some the latest sort of deep learning or machine learning, computer vision-based system, and use them to track all kinds of indicators that we might want to use to understand these very important sustainability problems, like, for example, tracking poverty with a very high spatial and temporal resolution. One of the challenges, the technical challenges that you encounter if you start thinking about these problems is that you typically need a lot of labeled training data to get these systems to work. Like Steve mentioned, if you want to teach a neural network to recognize images of cats and dogs, you have to show a lot of examples of what a cat and a dog looks like. And so in order to build systems that work for this kind of data and for these kind of outcomes that we care about, we need to develop new techniques because there is a huge data scarcity. We just don't have access to enough labeled training data to just take the latest convolutional neural network and train it off the shelf. So what we had to do is we have to come up with some new methods for training these systems and dealing with this data scarcity. And these include transfer learning and semi-supervised and weakly supervised learning. So in particular, for tracking and predicting poverty, what we did is we started with a transfer learning step. The idea is that while we don't have much information about these poverty outcomes, so asset-based or income-based measures of wealth, one thing that we do have access to is nighttime light intensity. It turns out that satellites are not only taking images of the world during day, but also during night. And if you look at how bright or not bright a location is during night, that can tell you a lot about how economically developed that area is. So for example, here you can see an image of the Korean peninsula taken during night, and you can see that there is a big difference between the southern part, South Korean, and the northern part, which is basically dark during night, right? So there is obviously a lot of correlation between economic development and the amount of nighttime light intensity that you see at different locations. So what we can do is we can exploit this extra information and set up a transfer learning task. What we're going to do is we're going to try to leverage this data, which is plentiful, and try to figure out whether we can train a neural network to take as input a satellite image of a daytime image of a given location and try to predict how dark or bright that location is going to be at night. So for example, if you see an image of a forest like here, then it's probably going to be pretty dark at night. While if you have an image of some kind of city, then it's probably going to be fairly bright at night. And so the idea is that if we can train our neural network to solve this task, then it sort of has to learn something about what kind of features to look for in the daytime images, right? It has to figure out that if there are trees, if it's a forest, then it's probably going to be dark, or if there are roads, if there are buildings, then that's a sign of economic development, of human infrastructure, and therefore it should predict high values. And the key thing is that we basically have an infinite amount of training data for this problem, right? We can just sample hundreds of millions of locations. We can get the corresponding daytime image, the corresponding nighttime image. We can set up an extremely large training set, and we can train a very, very large convolutional neural network to solve this task. And then what we do is we pre-train on this problem of predicting nighttime light intensity from daytime images, and then we do some simple standard kind of like transfer learning approach where we look at the kind of features that the neural network identifies as being predictive, and these are visual features that the neural network identifies as being predictive of nighttime light intensity, and then we hope that these features are going to be useful also for predicting poverty, let's say, which is what we care about in this case. So when we do that, when we train the model to predict nighttime light intensity, it turns out that it can do pretty well, and then we can try to visualize the features that the model has discovered in order to solve this task. And it turns out that the model discovers some features that are actually semantically meaningful. If you look at the filters, you look at what kind of pixels activate these filters, these features are meaningful. Like the model is looking for signs of infrastructure, things like roads, buildings, houses. My favorite one is a filter that has learned to recognize swimming pools. And so the model figured out that in order to predict nighttime light intensity, identifying swimming pools is actually a very useful visual cue because that probably corresponds to a fairly rich location that is going to be pretty bright during night. What's exciting here is that we didn't provide any label about what a road, what a house, what a swimming pool looks like. It actually figured that out by itself just by setting up this transfer learning task. In order to predict nighttime light intensity, it's useful to identify these kind of features, and so we were able to kind of get around the fact that we didn't have many labels and with this pre-training task. Now, that's the first step. Now, the other thing that we want to do is we want to be able to predict something that is We want to make predictions over space and time. We don't just want to make predictions independently for each image, which is typically the case when we think about computer vision problems. Here we want to be able to predict various kinds of economic development indicators over both space and time. So instead of making predictions independently at each location, what we do is we develop this kind of spatiotemporal model where we combine neural network feature extractors with Gaussian processes. These are standard models from machine learning and the geostatistics community. These are models that are used to essentially capture the fact that we have some prior knowledge about the things we're trying to predict. We know that the things we're trying to predict change slowly over space and time. We can capture that using this Gaussian process layer, developing some kind of end-to-end architecture that we can still train using gradient descent style models, but it captures this prior knowledge that we're looking for something that is changing slowly over space and time. The other interesting thing that we can do with this Gaussian process model is that it allows us to quantify uncertainty. This is important because first, we know how reliable our predictions are. The other thing that we can do is we can come up with a new semi-supervised learning method. The idea is that we have very few labels. We have very few labeled data, but we have a lot of unlabeled data. We have a lot of images, a lot of locations for which we don't have the corresponding labels. But what we can do is we can still try to leverage it using a new semi-supervised method that we developed. Let's see if it works. Yeah. And I'm not going to go into the details, but the idea is that because our model allows us to quantify uncertainty, given a location for which we don't have the corresponding label, the model will not only make a prediction, but it will also allow us to tell us how reliable that prediction is. And so what we can try to do is we can try to change the parameters of the model to make sure that the predictions are as reliable so that the variance in the predictive distribution is as small as possible. And that is a very, very useful regularizer. It turns out that it allows us to improve the predictive accuracy by a lot by taking advantage of the fact that we have a lot of unlabeled data that we can leverage in order to discover features. Intuitively, what is going on is that we're trying to force the model to look for features in the unlabeled data that are also present in the labeled part of the data. And that's a good regularizer because it prevents overfitting into features that are only present in the labeled part of the data. Now, if we combine all these things together, we get a model that we can then use to make predictions about how rich or poor, let's say, a location is, purely from satellite images. So what we can do is we can use the limited amount of training data that we have from our partners, or the World Bank, or USAID, and we can come up with a predictive model. So given a location, in this case, this is for Uganda. Here, each dot corresponds to a location for which we have survey data. We can collect images for that location. We can feed them into the model, and we can try to make a prediction for how rich or poor that location is. And so you can see here in this scatter plot, the observed, basically, asset score. This is a measure of how rich or poor that location is based on the kind of things people own in that village, compared to what we predict on the y-axis. So ideally, here you would want to be on the diagonal. We're not perfect, but we can do a pretty good job. We can explain something like 70% of the variation simply by looking at satellite images. And that was sort of unbelievable to our colleagues in the social sciences that we were working with. The best previous model was much, much worse than this. And so they couldn't believe that using these latest advances in computer vision and machine learning, we could get this kind of predictive accuracy just by looking at satellite images. Now, the nice thing we can do once we develop this model is that we now have a very scalable way for producing these very fine-grained maps of economic development for basically any country in the world. What we can do is we can take a country, in this case maybe Tanzania or Uganda. We can download hundreds of, or millions, let's say, of images to sort of like cover the entire country. We can feed them into the model, and we can come up with these very fine-grained estimates of how rich or poor different areas in those countries are. And what's nice about this thing is that the model is very inexpensive. The only thing that you need are images, which are updated frequently. They're getting better and better. And so we can keep these maps up to date in a very inexpensive way. So yeah, we got a lot of interest on this work from people like Bill Gates that was tweeting about this, to a number of organizations like World Bank, World Food Program, Department of State, and so forth. It was mentioned by the White House on the report on the future of AI. And we were also humbled to be selected by Scientific American as being one of the 10 world-changing ideas of 2016. So we're getting a lot of interest in this work, including from organizations that are really trying to use it to improve the way they make decisions, and both at the sort of like government level to small NGOs that are thinking about how to use this kind of information to make sure that they improve their operations and they can reach people that need it the most in a very inexpensive way. Now, these kind of ideas are not only limited to, they're not only applicable to poverty, you can apply them to a number of other problems. Here we also looked at food security challenges. That's another huge problem that is going to get worse and worse in the next 30 or 40 years. So there are a number of things you can look at by sort of like combining satellite images to kind of like try to predict food insecurity indicators or try to monitor agricultural outcomes. This is one of the things we try to do. We try to see whether it's possible to take remote sensing data, so again, images taken from satellites, from space, of the Earth, and try to use them to monitor agricultural productivity. So we built this system that takes as input images, a sequence of images taken from space of sort of like the whole United States, and then we use them to make predictions of how productive different counties in the US. We're looking at crop yields, we're looking at soybean and corn, and we're going to try to track over time and make predictions for how productive or not productive different counties are going to be in the United States. And it turns out that, again, we use a combination of deep learning and Gaussian processes to kind of model spatiotemporal correlation. And this model is extremely accurate. So here's an example of how well it does when you try to make predictions historically in the last 5 or 6 years. So if you try to make predictions in July for how the harvest is going to be at the end of the year, we get something like 5% mean absolute percent error, which is not great, but it's not too bad. If we compare to the predictions that we make in August, we get something like 3% error. And here we can compare to what USDA does. USDA is also producing these kind of forecasts. The way they do it is they have to call up farmers, they have to go in the fields, they have to collect samples. It's a very, very expensive kind of approach. And if we look at historically how well they did, well, they got something like 3.92% error, so they are actually doing slightly worse than what we can do in this much, much more scalable and inexpensive way, where we just need to look at images, feed them into our latest deep learning model, and make predictions. If we look at the predictions that we make in September, again, we can do slightly better than USDA. And then finally, in October, we do slightly worse. They start to perform better than us. But still, there is a lot of potential because our model is only requiring satellite images. So it's again, very scalable and very inexpensive. So this is the model we developed for the US, just because that's kind of like the most data-rich country that we could work on. But we're expanding this now in developing countries. We have a very good model for South America, for India. We're starting to develop models for Africa. We've actually submitted this to this competition that the World Bank held last year, the World Bank Big Data Innovation Challenge. And we were very happy to win the first place there with this model that we developed for predicting crop yields in developing countries. So they're, again, very, very excited about these technologies. They're thinking about how to use them to prevent food crisis, track various kinds of food security outcomes, and use them to improve their decision making. So again, this is not just limited to poverty and kind of like agricultural outcomes. We've also been looking recently at infrastructure quality. To what extent can we track how the quality of the infrastructure in different locations across the world. Again, we want to do it in an inexpensive and scalable way. So here you can see a map based on some survey data that is available in many African countries of whether or not different locations have access to electricity. So here blue means that that location has access to electricity, and green means that it doesn't have access to electricity. Again, you see that the data is sparse because that's kind of like what's available today. There's not a whole lot of information available on what kind of infrastructure quality people have access to in developing countries. Now, what we can try to do is we can try to make predictions based on our model. Again, we get a pretty accurate predictions. You can see the map on the right is what we can get if we feed a number of satellite images into our model. We can get fairly accurate predictions, both for electricity access, but also a number of other metrics like access to pipe water, sewage, garbage, and many others. So again, this is work under submission, under review, but it's pretty exciting that we can track all these outcomes in a very inexpensive way, because the idea is that we can scale up and we can expand the predictions to countries for which we don't have any data. We can keep them up to date. We can use them to improve decision making at various levels. So I think I'm pretty much out of time, so I'll just wrap up. I think this is a really exciting area to think about how to combine these new data sources that are kind of becoming available globally. Our global sensing capabilities are getting just better and better, both from satellites, but also phones, social media. We're getting access to a lot of data that is sort of like worldwide available, is cheap, is passively collected. It contains a lot of information about the health of our planet. And I think that there is a lot of potential for developing new AI and machine learning techniques to actually make sense of this data, extract actionable insights that we can use to come up with better solutions to these very important problems. So I think, yeah, I encourage you to think about these problems, because there is a lot of potential, and if we sort of like put together the latest advances in machine learning and computer vision with all these new inputs that are sort of becoming available globally, I think there is really a lot of potential for coming up with new innovative solutions to these problems. And that's it. Thank you. Yeah.
Great. Yeah, I have a question to start off with, which is in your in the model which accepts nighttime light intensity, are those images or are those ratings for like whole countries, or how does that actually get into the model?
So the night lights is basically you can think of it as another image of the whole world. At a certain kind of resolution. And so basically for a given area, there's a sensor that will measure how bright or not bright that area is going to be.
Same exact image footprint as the other image.
It's typically a lower resolution, but yeah.
Do you need to do any kind of special processing to like combine them, or?
You do need to do it. It's actually done for us by NASA, but yeah, you do need to basically pre-process it, take into account various kind of things like fires and other things that you need to take into account and basically normalize across latitudes and longitudes.
I see. That's interesting. So those are things that, so in some sense, like some other geographic information, like latitude, is also in some sense a kind of input.
Yeah.
As a low-level image processing input to the model.
Yeah.
Cool. Got it. Excellent. Other questions?
As you look at the data over time, how rapidly does the model change for what represents development over time? And is the model from today for the first world the best match against, let's say, a third world country? Or is the model from the first world from 10 or 15 years ago a better match against a third world country in predicting where they are today?
That's a great question, yeah. So at the moment, we don't use, tracking changes over time is something that it's pretty hard, and it's especially hard to, so we have a model that can do it, but it's hard to evaluate because the data it's typically not a panel, but it's a survey. So for this, we don't get to see how a particular location changes over time. Like they sample different locations every year. And so it's very, very hard we don't have ground truth data to evaluate how well the model does. Like the only way we can do it is by aggregating spatially, and it does pretty well, but we don't know exactly how well it does at very fine-grained kind of like resolutions. In terms of how well the model transfers, I don't know whether you would be able to use a model, say, from the first world country and transfer it to a different one. We tried it in the context of Africa. What we did is we trained a model in one country and we tested it in a different one, and that kind of works reasonably well, as you would expect. Like if you try to go from East Africa to West Africa, it's not going to work as well as if you try to do it based on a neighboring country. I think, there is a lot more to explore there in terms of like scaling up globally. At the moment, we're just focused on Africa, but we're going to have to think about how to extend it to, say, Southeast Asia, South America, and other countries. I should say, the World Bank is also developing this. They developed this model they've re-implemented it. I know they have some pretty good results in Mexico. So they've been able to do it. So it doesn't just work in Africa, but people are starting to sort of like implement it in different parts of the world. But indeed, there is more work to do in trying to think about how to transfer knowledge from one country to another. We did a little bit of this for the crop yields when we try to make a model that should work well, say in Africa, where we have very limited data. We sort of need to pre-train, say in the US or Argentina, and then transfer there. But then there are challenges in terms of like different seasons and different pre-processing that you need to do to get it to work.
Regarding the poverty model, so if you use the nighttime lighting to train the model, then what made it work better than the original nighttime lighting data?
Good question, yeah. So the question is, well, what would happen if you just use nighttime light intensity? So that was kind of like what people used to do before. The problem is that there are many locations that are completely dark at night, but there is a lot of variation, say, in how rich or poor these locations are. And so if you just use the model based on nighttime light intensity, you can basically don't see any variation because the locations are completely dark, so you don't have any predictive power. Then if you look at the images at these locations during day, you see that there are differences. There are differences in the kind of infrastructure that they have. There are many visual cues that you might be able to use to still get some kind of predictive power on those lowest, the poorest kind of like percentiles of the population. So that's partially where the increased predictive power of a model comes from.
So do you know where the proposal of a NightSat stands? I know the NightSat people came by Ames a couple of years ago to go to the National Science Foundation and try to promote a night-based satellite. But up until that point in time, the remote sensing community is pretty negative against flying things on the dark side of the Earth.
I don't know what happened to there. I think what's exciting these days is that there are a lot of private companies that are entering the market, like Planet, for example, here in the Bay Area. So I think why I think these problems are interesting is it's not only just something that that only the intelligence community has access to or only the governments have access to. It's becoming relatively cheap to send out satellites because of companies like SpaceX. There are a number of private companies that are developing their own satellites. They are sending up there. Planet has hundreds of little small doves, like little small factor satellites, basically just a camera that they send into space. And so, they are getting, I think, they are getting something like they are able to get an image of the whole world at something every day at something like 3-4 meter resolution. And so, and this is a private company, so you don't necessarily have to rely anymore on government to send out these satellites. It's becoming so cheap that even private companies have the means to, even startups have the means to do these kind of things these days.